Hello everyone. Nice to see you all. It's a pity that it has to be through a screen, but circumstances are circumstances. I hope we can soon meet physically. Well, first of all, I want to congratulate all my colleagues at the MIP. I was really impressed by your results. And yeah, I want to wish you all the strength for the last lap of this adventure. And yeah, wish you all the best of the luck for your thesis defenses. So for those of you external to the MIP network, let me introduce a little bit myself. My name is Javier Nistal. I'm a PhD candidate at Telecom Paris and an assistant researcher at Sony Computer Science Labs. So before joining this project, I worked for a bit in industry in different MIR projects, and I studied my academic background is in telecommunications engineering, where I studied at the Polytechnic University of Madrid, and followed by the Master in Sound and Music Computing from the Music Technology Group in Barcelona. So today I will be presenting a comprehensive but brief overview of the research that I have carried out for the last 3 years as part of my PhD. I will focus mainly on the results, so we will listen a lot of audio examples. And the title of the thesis is Exploring Generative Adversarial Networks for Controllable Musical Audio Synthesis. So this work was carried out under the supervision of Professor Gaël Richard, Director of HiParis and Professor at Telecom IP Paris, and from the industry side, Dr. Stefan Lackner, Assistant Researcher at Sony CSL's music team. So let me start by introducing and motivating a little bit the topic. Audio synthesizers are electronic musical instruments that generate artificial sounds under some parametric control. They became popular during the 70s after some technological breakthroughs that enabled their mass production. Today, their use is widespread across a variety of music genres, and in fact, many of these exist thanks to synthesizers. But not only they have influenced the music we make, but also how we make it by inspiring novel paradigms for musical expression and creation. So synthesizers have indeed evolved from those once bulky machines of the size of a room into more compact, powerful, and flexible digital tools. However, two fundamental challenges are still unresolved. One is the development of truly user-driven synthesis systems that respond to semantically intuitive parameters. So as we can see in the picture of the slide, where very common, this is a version of the DX7 software version, and we can see that modern synthesizers still afford the same old parameters from their analog ancestors, which are based in oscillators, filters, modulations, and so on. All these means of control, while they are nice and they have undoubtedly sparked the creativity of many famous music artists that they use them, they respond to signal processing principles that require a very solid understanding to purposely drive the system towards a specific sound. This ends up by obscuring the music creation process. The second challenge is designing universal and source-agnostic synthesis systems that can model any type of sound. So there are many synthesis techniques out there for audio synthesis, each of one with its own sonic flavor and offering very specific parameters. This means that musicians will need to acquire many types of synthesizers for specific musical purposes and consequently master their different underlying parameters based on the synthesis techniques. Also, there are many sounds that current synthesizers fail to model, like explosions, gunshots, and therefore we need to rely on large sample banks to use these on our creation process. So this seems like an important problems to be addressed, and luckily for us, the field of deep learning offers promising data-driven approaches that may pave the way towards building such type of systems. So given a large enough data set, in principle, generative neural networks should be able to model any type of sound, and also in principle, they should allow for any interaction protocol. So we just have to gather a lot of data and then train the neural network to learn whatever relationships there might exist between the input control signal that we want to use to parameterize our neural network and the output data, in our case, audio, that we want to generate. So in particular, in this thesis, we are interested on a specific type of generative neural networks, which are called Generative Adversarial Networks, or GANs for simplification, but I won't go into detail about them. I will just mention that GANs have been proven very successful at generating high-dimensional data, such is the case of image, but also in audio, and also in a short amount of time compared to other generative neural networks, such as autoregressive models. They can also learn very high-level parameters, both in a supervised and a non-supervised way. So, for example, they can generate new human faces based on abstract features, such as the pose, the skin color, or some hairstyle. And also, given some sketch landscape, they can render a plausible high-definition version of it. So the goal of this thesis is to study the use of GANs for musical and controllable audio synthesis, and our aim is to develop novel tools for music production that can offer intuitive and at the same time expressive means of sound manipulation. So our hope is to bridge the semantic gap that exists between modern synthesis parameters and the artist's unstructured musical idea that ultimately drives the creative process. So to put it a bit in a more poetic way, in words of composer Edgar Varese, I dream of instruments obedient to our thought and which with their contribution of a whole new world of unsuspected sounds will lend themselves to the exigencies of our inner rhythm. So the thesis is organized into 6 articles, the first 4 of which correspond to the main contribution of this thesis and cover general audio synthesis tasks with GANs. The last 2 are collaboration journal articles, the first one focusing on audio enhancement of MP3 music using GANs, and the second one, I won't reveal the title nor the authors because it's under review. It just mentions our experience when working with musicians in the context of technology creation for music production. So basically, we report on our experience dealing with music creators from their experience using the tools we create. So our first paper was published at the European Signal Processing Conference last year, and it is entitled Comparing Representations for Audio Synthesis Using GANs. So this initial work studies the performance of GANs when trained on various common audio signal representations, including the raw audio waveform and several time frequency representations like the magnitude and the instantaneous frequency and the phase, several implementations of the CQT, the complex value SDFT, and many more. We compare this in the context of synthesizing tonal instrument sounds like flutes, violins, guitars, etc., taken from the NSynth dataset, and we conclude that the magnitude and the instantaneous frequency of the SDFT work the best, which confirms results from previous works. But also, we, as a novelty, we point out to the complex version of the SDFT, which has yielded very good results. Let's listen to some examples. So here we have some random generations. We can also do the interpolations on the latent space of the GAN. We condition the model specifically on pitch information, so we can control this independently from other information. This allows us to perform scales. So on, and the same way we can just take a music piece in the form of MIDI and take the sequence of pitches to condition the GAN and create music. So we have more examples in our webpage. Feel free to go and skim over them. So our second paper builds on top of this previous initial work, and it was published at ISMIR last year, and it's entitled Drum GAN Synthesis of Drum Sounds with Timbral Feature Conditioning using Generative Adversarial Networks. So Drum GAN is an audio synthesizer of percussive sounds that can be controlled based on perceptual parameters such as boominess and other timbral features described in a European project called the Audio Commons. So this project released some publicly available perceptual models of timbre that provide continuous features for such sound properties. So in this work, what we do is to take a large data set of kicks, snares, and cymbals. We extract features using these perceptual models, and then we simply use this as conditioning information to our GAN during training. So the work concludes that the conditioning features help to generate better quality samples, And also some degree of control over these features is obtained. Although afterwards, we created, as a result of this work, we created several versions of VST plugins. And we empirically, by working with artists, we really found quite useless this perceptual conditioning, although it's responsive somehow, but in terms of creating music, it didn't seem very valuable. But let's still listen to some examples of this version of DrumCam. So these are, oopsie. So these are some, we gave to some music producer a pool of generated sounds with DrumCam, and he created these loops. And yeah, this last one. So just a few details. This was trained on the complex representation, and also these generations are at 16 kilohertz. So on next iterations of this plugin, we included an encoder into the GAN latent space that allows us to generate variations of existing sounds, and that we did in collaboration with one of our interns. And also we scaled down the previous versions we scaled up in order to work with full resolution audio. So this current version is generating 44.1 kilohertz sample rate. Also, I want to take the chance to thank Sigan Awamer, one of my colleagues at CSL that took care of building this nice interface. So let's go for it. Let's listen to this demo of the latest DrumCam version. So we can interpolate it continuously between different instruments, so kind of a sense of kickness and snareness attributes. Same with cymbal. And now you will see how we can encode sounds into this latent space by just drag and drop to a clap. We drag and drop. The same with other sounds, even those that are not in the dataset, more or less. Shaker. And create variations. So in this line, another example I want to show you. So CA Carr from DataBots recently had some conversations with Stefan Ladner, and he was curious about how DrumCam could perform with beatbox recordings. So he actually sent us some beatbox recording. Let's listen to it. So this is CA Carr making some beatbox.
It's called music. But teach it to your kids when they're 4. It's called music.
So you get the idea. So Stefan ran some onset detection on this track and fed each of the slices into the encoder and decoded it back. And let's listen to the result. We will listen to the original beatbox with on top the decoded audio.
It's called music. But teach it to your kids when they're 4. It's called music. But teach it to your kids when they're 4. It's called music.
So yeah, pretty fun. So in also another nice result from DrumCam. So at Sony CSL, we work in close collaboration with artists, and I had the chance to meet a Sony ATV artist 29, which is a hip hop producer, and he showed a lot of interest on DrumCam. And as far as I know, I believe he uses it quite often in his production setting. And he released a drum bank collection, which is publicly available. I encourage you to use it in your research or in your music. And yeah, he released this curated sample bank created with generations from drum bands. So let's listen to the teaser that we released to publish this drum kit. So yeah, the drum kit is composed of 125 drums with a wide variety of classes, all of them curated by 29 with generations of drum. So one last project I want to mention from DrumGun, branching from DrumGun, and very, very freaky project. It's called Chainsaw Gun, and which is a synthesizer of chainsaw sounds that it is meant to be used for the soundtrack of the Japanese anime, The Chainsaw Man. So this crazy composer from Japan reaches out, and he asked us to develop some sort of synthesizer of chainsaws to use on his creations, and this is what we did for him. So yeah, pretty fun. And it's actually nice to see that actually guns can work in a wide variety of acoustic sources. Okay, so let's go to our third article, which was accepted for publication at ISMIR 2021, and I will be actually presenting in the following weeks. And it is entitled DARKGAN, Exploiting Knowledge Distillation for Comprehensible Audio Synthesis with GANs. So this work tries to overcome the scarcity of annotations in musical audio datasets by simply generating them with a pre-trained audio tagging system. So DARKGAN is a synthesizer of tonal sounds that employs the output probabilities of such tagging system as conditional information. This process is called knowledge distillation, and we use it to control the GAN based on attributes from the audio scent ontology, which provide description for attributes such as bicycle bell, engine, alarm, sonar, and up to 600 attributes, from which we only use 128. Now, the fun part of knowledge distillation is that it enables the GAN to learn representations of attributes that do not explicitly exist in the training data, but are somehow sparsely encoded across many examples. So this hidden information was coined by the very famous work of Geoffrey Hinton on knowledge distillation, which is called dark knowledge. So this allows, for instance, to transform an initial string-like sound generated by DARKGAN. So we can transform it into a sonar sound by just simply raising the parameter associated with its attribute. Even though there are no sonar examples in the dataset used to train the GAN. The same for other attributes, kick drum. The bass guitar looks more like an organ, but and also the mantra attribute. Pretty fun. So our fourth article was published at WASPA 2021, and it is entitled VQCPC GAN, Variable Length Adversarial Audio Synthesis using Vector Quantized Contrastive Predictive Coding. So one limitation of most applications of GANs to audio synthesis is that they can only generate audio of fixed duration. While this is a natural choice for images, in music, we are generally interested in generating sounds of any durations, of course. And the main problem with GANs is that it is not obvious on how to allow sequential generation while preserving the global coherence of across the whole generation span. To do so, in this paper, we implement a framework on synthesis of tonal sounds that by conditioning the model on two types of features. sequential features that we learn through self-supervised learning techniques. That's why the BQCPC part in the name of the model. I won't go into details about BQCPC. We can discuss it afterward if you want. But these BQCPC features give a condensed representation that capture dynamic aspects of the generated content. Also, global features that encourage the global consistency, global consistency across the whole generation span. So these are, for instance, the pitch that encourages to all the steps at the generation time to belong to the same pitch class, and also the random noise, which is characteristic in GANs, that we use it as global conditioning by repeating it across all the generation steps. And basically, this noise captures the remaining information that it is not covered by the rest of the conditional features, which happens to be timbre. So let's listen to some examples. These are generations of 0.5 seconds. For 1 second. And for 2 seconds. So note that in order to generate longer or shorter audio, what we just do is to respectively upsample or downsample this sequence of BQCPC tokens. So we evaluated the models against some baselines trained to generate fixed duration audio. And while we observe a lower audio quality in BQCPC GAN, we can competitively generate audio of any duration, and also with, as you can see, with global consistency. So our fifth article was published at MDPI Electronics this year, and it is entitled "A Stochastic Restoration of Heavily Compressed Musical Audio Using Generative Adversarial Networks." This work was originally meant as a pretest task for learning more complex musical relationships in the future. So, for example, imagine that we want to generate some drum pattern given the recording of a bass line. So this is a very ambitious task for a first attempt, particularly because gathering a large-scale data set of aligned multi-track sessions is not an easy job. So this is a large data set where I have bass lines with their accompanying drum recordings, and this is not easy to collect. Therefore, we thought that an approximate and much more simpler task to do could be to just try to restore highly compressed musical audio, where we can just simulate the compression and just generate as much data as we would like. So concretely, we study whether a GAN generator conditioned on highly compressed musical audio signals can generate outputs resembling the original high quality uncompressed audio. So results show that the GAN can improve the quality of the audio signals for very highly compressed MP3 versions, but for those that are less compressed, it doesn't really improve at all. But let's listen to some examples. So this is the original WAV audio for a specific excerpt. And I mean it from the bar. This is the MP3 version of it at lowest, at maximum compression rate. And I mean it from the bar. And this is the restored version. And I mean it from the bar. The same for a bit less compressed audio, wave file. The MP3 version. And the reconstructed. So as we can see, the GAN can indeed generate some missing content. Yet what we observe is that it tends to be quite noisy, whatever it's generated. It's positioned in the right position in the spectrogram, but this model fails to really capture harmonic components with the showing structure with respect to the conditional content. So this is all from my side. Let me conclude with some observation. some observations. We investigated different forms of audio data for audio synthesis with GANs, and we concluded that as a novelty, the complex value STFT works very nice, and also that the magnitude and the instantaneous frequency of the phase corroborating previous findings on other works on audio synthesis with GANs. We explored different means of conditioning the GAN in order to steer the synthesis based on perceptual or semantically meaningful attributes. We proposed a self-supervised framework for generating audio of any duration. We also showed that GANs can deal with various sorts of audio sources, like chainsaws, percussive sounds, and tonal sounds, and also learn complex audio transformation up to a certain extent. We developed novel and intuitive tools for music audio synthesis that are being used currently by professional artists to create music that it is commercially viable, which is very valuable for us because we want to develop tools for music creation. So that's all from my side. Thank you very much. If you have any questions, I will be very happy to answer them.